Hi and welcome back. So in this video we're going to do problem number 28 out of Recitation 1 from Signals. And the problem is which of, which of the following three curves is most likely the plot of cosine of 2 pi t minus 2. And now we're given these three plots. So the way I like to do these is I like to figure out, well, any general cosine we have is determined by k cosine omega t plus the phase. If we can figure out k, omega, and the phase, these three variables define what the cosine is. If a cosine has a unique k, a unique omega, and a unique phi, that's a unique cosine. If I vary any of these variables, it changes the cosine somehow. So now let's start out looking at k. So k for all of these, hopefully you can see. Let me write down. For k, hopefully you can see k determines the amplitude we would have, and my amplitude here is 1. The 1 is the k for this particular cosine we want, cosine 2 pi t minus 2. And all of these cosines oscillate between 1 and negative 1. So not only are, so they're all the same basically. All of these cosines, k is equal to 1. So we can't even eliminate any cosine here. We know that k for all of these cosines is equal to 1. So now let's try to determine omega for each of these cosines. And the way I like to determine omega is the easiest way to see omega on a graph like this is to look at period rather than frequency. If we can figure out how much time is between each of these two peaks, then that's going to be a much better measurement of omega than trying to determine omega any other way. If we can figure out what the time is between our high peaks, then that's going to be a very good way of figuring out what the omega is for these functions. So if we remember, omega is equal to 2 pi times f, and f is equal to 1 over t, we can say omega is equal to 2 pi 1 over t, multiply both sides by t, so I have t is equal to 2 pi over omega. So now the particular omega we have in this problem is 2 pi, right? We've got 2 pi. 2 pi is our omega. So we are looking for, if we substitute in 2 pi into this expression, 2 pi divided by 2 pi, that cancels. We are looking for something with a period of 1. So if we look at this, it looks like that first peak is, I don't know, maybe around like, say 0.3. And it looks like this peak is around like 1.3. So that t, it looks like, is about 1. And it looks like this peak is a little past 0.6. That peak is a little past 1.6. It looks like that period is also 1. And then finally, it looks like that period's right at 0.8. That peak is right at 1.8. This t is also, that period is also equal to 1. So all of the omegas here, the periods are all the same, which by definition means that our omegas are all the same. Our omegas for each of these functions, if the period is 1, our omega for each of these functions is equal to 2 pi. So again, we can't eliminate any single one of these functions where all of the omegas for every single one of these functions is equal to 2 pi, and all the periods for each of these functions is equal to 1. So now we figured out we can't use k, we can't use omega, so we are going to have to use phi. We are going to have to use the phase shift to figure out what our which cosine is 2 pi t minus 2. So now there are a number of different ways you could do this. One way we could do it is we could say, okay, if I have cosine Yeah, let me leave the k. K cosine omega t plus phi. If I wanted to factor an omega out of this, I could get k cosine, or factor the omega out of the inside, omega times t plus phi over omega. So now everything inside this kind of nested paren we've got is time. Instead of having radians in there, we now have got time as our argument inside of this parentheses. So now if we can figure out basically what our time shift is. If we just had t and our phi over omega was 0, we would have, or if phi was just 0, we would have no time shift. So if we take t plus, if we take this phi divided by omega, we take phi divided by omega, that's going to give us our time shift. That's going to give us our time shift. And hopefully this isn't the first time you've seen this. We went over this in lecture. I think it's probably even the first lecture, if you want to rewatch that lecture to get more in depth into that. But our phi divided by omega is going to give us the time shift that we're looking for. And we can tell by inspection here, that's how these graphs vary. This one's first peak is there. This one's first peak is way past. This one's peak is even further past. So we have variation of the phase shift. So we know that that's what we're going to have to figure out in order to tell these graphs apart from each other. So our time shift, and also we've got a minus time shift, which means that we shift our cosine to the right. And we can also see that all these cosines, it looks like they're shifting to the right. So if we do phi divide by omega, that gives us our time shift. Our phi that we're looking for is 2, so we do 2 divide by our omega, which is 2 pi. That gives us our time shift. And even our phi is negative, so I'll put a negative here. And I'll have a negative time shift, which basically means I need to shift this to the right. And all these shift to the right. So anyway, the 2's cancel, and I'm left with minus 1 over pi. Now I'm going to get out the calculator and just do 1 divide by pi. I get 0.318 seconds. So my time shift that I'm looking for is minus 0.318 seconds. And it looks like this one, that's like 0.6 something. This is 0.8 something. And this one, it looks like, is 0.3 something. So for those reasons, I'm going to say that graph A, or for this reason, because of the time shift, I'm going to say that graph A is most likely the plot of the cosine of 2 pi t minus 2. So that is our answer. Our answer is graph A. So thanks for watching, and I'll see you in a future video.